Hello everyone, this is the FOSS4G. We are today in Thursday in the Humahua classroom, and we will be having now the last talk from of the day with Andrea Antonello, who will be presenting integrated modeling with k.LAB. Thank you, Andrea. Is that yours?
Okay, thank you very much. Thanks to everyone who had still the energy to come to the last talk of the day. And I'll be introducing you to, or at least I'll try to introduce you to the world of integrated modeling with k.LAB. And today I'm wearing the hat for, I'm talking as a member of a project called AREAS, which stands for Artificial Intelligence for Environment and Sustainability. To better get an idea where I'm coming from, I'd like to go back kind of 20 years because that's the time when I started to do environmental modeling. And at that time, I was working at a university department, and together with the professor, we were always discussing what would be the best tool to do integrated modeling. And we were working on geomorphology, hydrology, and we're dreaming about connecting models with other models like groundwater or meteorological model, evapotranspiration, or kind of just describe the whole environment, right? And in the end, we came to the point where we said, okay, as you might guess, that tool has to be a GIS, because at least we're talking 20 years ago, at least that tool would harmonize the spatial context, which is not cheap. So I spent kind of the 20 years after that, up to now, my whole professional life trying to integrate. So if you look at the timeline, you will see different GIS, different modeling frameworks, so like OpenMI, OMS, or the GIS. Not just me, but me and my colleagues, we're trying to integrate with other tools in which we could share models together. So the dream was kind of like to be able like sharing deals model like we did back then when we were kids with stickers. I have a sticker double, so I give you mine, you have one triple, you give me yours, and trying to reach all together the same full set of stickers. And that would be right now like being able to share models. And with the FAIR principles and with free and open source software, this should just be possible, right? Actually, it's a bit difficult, and I can tell you in the last 20 years I've seen that a lot, because modeling is something particular. You have your project, you do some model that does some strange stuff nobody understands, but it might save the world. So what is the common practice? The modeler takes a core algorithm, which is, let's say, 10% of what will in the end be there, and it then decides, oh, I have to read a raster, yes, and a vector, and I have to read I don't know, rainfall data, discharge data, online services. And so this is a whole boilerplate of IO. And then, well, the results have to be visualized clearly. So then there is visualization code. And finally, there is also a timeline to follow, because my model does simulate the timeline. So inside the model, you have static parts and the dynamic parts. And so you start putting in tricks to make it work along a timeline. And in the end, you end up with a nice monolithic stuff that really works really good. And you can publish, and that's very cool. But it works just for those cases where the end result counts. So if instead you just want to share and connect model, because in that case, extracting what was the core algorithm is extremely difficult. And so it's very difficult to join models from different sources. So how is k.LAB different, and how is it supposed to help you? Well, k.LAB forces you to just create the smallest possible entities, quantums of knowledge that just incarnate and represent a concept. And k.LAB then gives you a resolver that takes all these quanta of knowledge and makes them compete to best explain the requested observation. And all of that is then assembled into a data flow that will contain the best possible strategy to get to the result. Well, I don't know if you were following me. What does that even mean? Let's take it a step at a time. First, I would like to tell you what AREAS is and how k.LAB got born. we are dating back in 2007, so it's quite some time, when Professor Ferdinando Villa, the visionary and developer, still yet the main developer of k.LAB, started a project with a fund of the National Science Foundation at the University of Vermont. Throughout the years, several players contributed and funded the project, and in around 2012, Professor Villa decided to move back, since he's an Italian, back to Europe, and he ended up being at the Basque Center for Climate Change. And that's right now kind of the headquarters of AREAS and k.LAB. But AREAS is not just a project, it's a network of scientists. And this is the breaking point that in 20 years I've never seen before. What I've seen in AREAS is a lot of scientists that collect data, that collect models, and that put them in a network, which is what is called the integrated modeling network. And in there, in what we will see is k.LAB models, data sets, and whatever processing power is set and made available to whoever wants to enter and model with it. You know what AREAS is now, and what's k.LAB? k.LAB is just a software, yeah, kind of a big software. It's a full stack solution that helps modeler to do integrated modeling. So it supports production, curating, linking, deployment of scientific artifacts. That could be data sets and models. And it's just a system to observe the world, the whole world. So not just your little piece of watershed you want to analyze, but it wants to observe the whole world, and it wants to build and extend the world. So I hope behind of some of the screens that are listening now, there is someone who's saying, yeah, hell, where are my ontologies? You can't do this without ontologies. You can't describe a world without ontologies, because you need validation. And yes, you're right, because ontologies are really a necessary ugliness. I've hated them for long. I've never made them enough. And therefore, I love k.LAB, because in k.LAB, what happens is that ontologies are buried under a semantic layer of a near natural language. What does that mean? That a user can just approach, ask a question in English, and the system will resolve the query into a data flow. And throughout this resolution, it will go down the tree of the concepts and the dependencies of the concepts until it gets down to the ontologies, where it validates everything. So what happens in the k.LAB platform is that whatever is produced is also validated. But let's have a look what the platform looks like. There are 5 components, and 3 are server components, the engine, the nodes, and the hub, and 2 client components, Explorer and Modeler. The engine is kind of the heart of the platform. It takes care of the resolution of the whole reasoning to convert the user query into that particular data flow that can be executed and then gives a result. The nodes instead are components, server components, that are distributed and that contain the knowledge, scientific knowledge, that any partner can set up a node and can put knowledge in it, being it resources like data or equations, or semantic layer, which is where resources get coupled with concepts, which means they are semantically annotated, and this is where everything gets its meaning. So it's no longer just a resource, it's something that has a meaning and that can concur in the resolution process. And then there is the reactivity layer, where, well, things get to life, really, because you can attach behavior to scientific artifacts and create simulations. The hub is basically an authentication server that organizes the nodes. Very important, we'll see later why, is that it gives you, it manages certificates, and with those certificates, you are part of groups, and you can access a worldview. But that later. So Explorer and Modeler, one is a web application that allows end users to just ask the particular question we were talking about, and the Modeler is something more advanced, where modelers can just develop models, and publish resources. Something like this. This is an editor where you can load a resource in, being a shapefile, a TIFF, or something, even a WCS server or a WMS server. And then here you can add documentation, license, time, space of validity, and you can publish it to a node. So how can you do to try that out? Well, you need two things. One is the control center that you can get at this link of the Getting Started in the Integrated Modeling webpage. And you need a certificate to access the Integrated Modeling Partnership Network, because otherwise you won't have a world with which you can model. So this is how the control center looks like. You can start a local engine that you can locally use on your computer, and you can start a modeler. And from there, you can finally open the Explorer, which looks like this. This assume if this is an application, an installation, end users would just see this or a customized version of this. The modeler is just used for the modeler application is just used for modelers to develop stuff. So let's have a look how this works. You can start writing your question. I don't know. You want what do you want to observe? Like elevation. You start writing ele, and the system gives you some hint of possible observations that are available, like events, election, or qualities like elevation. And if you continue writing or select elevation, for example, what happens, the resolution process pulls out the resources that best represent the observation. In that case, a digital elevation model, clearly. But you can also enhance it a little, and you can say like elevation, minor or major. You can add some simple arithmetic operators, and which would result in a map with just elevation major than 1000. You can also use semantics operators, which are keywords or group of keywords that have the ability to transform concepts into different concepts, like distance of city, which generates in a map that, a raster map that has in every point the distance from the nearest city. And interesting is that there is a main concept that is observed, but every observation that is generated during the resolution process and the data flow execution is added as a secondary output. As you can see in the lower part, I don't know if this is visible, in the lower part, the 3 cities that were in the current scope, in the current context, are also listed. Everything can be downloaded as shapefiles as TIFFs. Let's have a look at another, like present of mountain peaks. And that will pull all the mountain peaks that are available. But you can do also something a bit more complex, like I want to see the land cover type, but without water bodies. And in that case, you can see there is a map of land cover type, but the water bodies are being left out. There is a moment in which the Explorer comes to its limit, and you need something bigger, and that's where the modeler comes into the game, which is this. And I want just to spend a second about what you can also see in the modeler, which is the worldview. The worldview is basically everything you need, every word you need to be able to model your own models. So if we're talking about a region, who did describe a region? It was described by a community who carefully designed this worldview, and a region anything needs to be described. So for example, a region is an aerial location. And if you click on it in the modeler, you will be led to, for example, aerial. And it boils down, every concept needs to be described. And in the end, at some point, you come, for example, like aerial, you come to the point where you see written, concept is core observation. And this core observation is where k.LAB connects to the ontology. This means the ontology is then get from the beautiful old files, and the validation is done by k.LAB. So this is the beautiful thing of k.LAB. You can use a natural language, but then someone else did for you the whole stuff for linking it to ontologies and activating validation. So let's get back to the fun stuff. Well, with the modeler, you can write more complex stuff. You can just use the model keyword. And if you want to look to observe a different thing like level of elevation, which then gets a new quality, a new concept, then you can say model the level of elevation, observing clearly the elevation, but using as a lookup table the elevation divided in certain classes. And when you write that down and you execute it, you will get a map that is classified following your particular table. And if you want to observe just a particular region, you can use this observe keyword and define a region with a particular resolution or projection. And when you run that again, it will just concentrate on that region. We were talking about the FAIR principle, so we should find and understand how everything happens. And here in the tab above the elevation level map, there are other tabs that you can click and where you can have a look at the data and the data flow. So every time you run a model, it is possible to check which data sets have been used for the resolution. So in that case, it was a simple elevation model. So it's an SRTM on global scale. You see also the coverage of the data set. And you can look at the data flow also. And the data flow, which in this case is very simple, it tells you that it was pulling a WCS resource to take the elevation, and then it applied the lookup table. And if you click on the lookup table on the right side, you will see what the lookup table was. So we're talking global. So what about data harmonization? Because it's a mess when you want to model the whole world, because most of the data sets are not global. So what happens at borders? One good example is the land cover type. If you do it in this area, you will notice that there are more data sets involved. And if you look at the tab with the data sets, you see that it's Korean and it's an ESA Climate Change Initiative land cover. And if you look at the data flow, well, it's interesting because it will tell you that it had to merge different resources, but these resources are with a different classification. So how can this be done? So you click on the classify part of both flows, and you will notice that the different classes have been decoded to the right internal attribute. And where are these attributes? Well, these attributes are in the worldview clearly, because somewhere they have been defined, and k.LAB will just talk the right class out of it. So what about time? We have processes that can define operations in time. One example is the weather process that is able to create observations of rainfall, temperature, and as you can see, minimum temperature. There is no such thing like a minimum temperature as a single word. No, it's a minimum temperature, like you would speak it out. So this is how it looks like, and you will have a dynamic version of the map that you can then scroll through. But the real important thing is that these maps, these processes, can be then used inside of more complex models. In this case, for example, this is a hydrological model, an infiltration model, for example, or a base flow model. You can see here runoff, evapotranspiration. They all depend on each other. And you can just concentrate in writing the part that defines the runoff, the evapotranspiration. You don't have to care about the water volume, the rainfall volume, about curve number, the crop coefficient. These are all things that come from models already existing in the network. And the result is that when you run such a model, it will generate in the data flow a huge data flow where you connect to the different services in the end, to the resources, or to models that generate. For example, a stream network is created by creating a flow directions map, then a contributing area, then you extract a network, and so on. And everything, whenever you run this model, is run into a flow to give you the result. For example, also, if you don't have a map of crop coefficients, then you could have this tiny little model that you can define in place. You model the crop coefficient observing an NDVI, a normalized difference vegetation index, and you set it to that particular thing. It's just a simple equation. So if there is no crop coefficients map, but this model has been published into your network, it will just use that one. The resolution process will decide which resources it's better to pull for that particular use case. So I think I'm done, and I should be more or less in time. So I leave you with 2 more slides. One for developers, because you will ask yourself, where is the source code for all this? There's an umbrella organization on Bitbucket called Integrated Modeling, and it contains kind of everything. We should be having a mirror on GitHub also. So, well, we'll keep you updated on that. But you find everything, the engine, the modeler, you find a bunch of examples, and most important, you find a worldview, because the worldview is, in my opinion, the most difficult thing to do in all this. So thanks for being here. If you're interested, since this presentation didn't even scratch the surface of what k.LAB is able to do, it has been adapted for a more GIS audience, because that's more or less my expertise. Please have a look at the presentation of the Areas for Sea Explorer at the UN, because there has been a huge launch of this application for capital accounting. So please have a look at that, where Ferdinando Villa really explain you the whole nice candies that are behind k.LAB. If you want to collaborate, just get in touch at the link you see down there. Thank you very much for being here.
Hi, Andrea, and thank you very much for your talk. I was really impressed by k.LAB, to be honest.
Thank you. Good.
And we have some time for Q&A. Our first question is this one. How is the documentation? A college discovered and got excited about k.LAB, but when I looked at it, I couldn't find much documentation for the KIM language.
Okay, that's right. The good thing is that the collaboration with the UN launched a whole forced kind of a whole documentation process. So I missed to put the link in it, and I'm very sorry about that. But there is already some documentation online, and I will, I don't know exactly how to get it right now, but I will post it maybe on Twitter, where you can get a whole idea about what k.LAB is and how the technical details also about KIM. I have to admit that the best way to learn KIM is with the examples project. I placed the source code in, because in there are examples and test cases that explain exactly how to write particular situations. I would honestly, that's how I did it. I started from the examples, and since it's quite a natural language, you get, for simple things, you get very quickly up and running.
Thank you very much. I was just posting your Twitter handle in the chat so people can contact you if they want.
Thank you very much.
Let's see. There are no more questions. We can wait a little bit or call it here. Let's give it a few seconds because there is a lot of delay in the stream.
Oh, okay.
Well, seems like there are no more questions, so we can end here maybe. Thank you very much, Andrea, for your talk.
Perfect. It's been a pleasure for me. Have a nice evening all.
Thank you.
Maybe I see you at the gala dinner in a couple of minutes.
Yes, I hope. See you then.
Okay.